learning objectives. Define refraction of a wave. Graphically demonstrate the behavior of a refracted wave to predict its direction. Verify the law of refraction through an experimental lab, and do practice problems. Refraction is the change in direction of a wave when it's traveling through different materials, like a pencil immersed in water, or through the same material but with different speed, like water waves when it's moving from deep water, from shallow water, or from shallow water to deep water. The median is the same, is water, but the wave change speed. So that's why refract. In this case, we have two different medians. So that's why the light refract as well. Here the light refraction, and this is water refraction. Now this guy is trying to catch his dinner. So he is looking the fish at the wrong location. The reason is he's not considering that the light is going to refract and form an image in another location. So what's going on here? First, let's define there are two different median. It is defined by this boundary. Here we have our normal line for the graphic representation of refraction and reflection of a wave. Is really important to define the normal line. The normal line is an imaginary line that is always perpendicular to the boundary, which means that the line that defines the two different medians. So now let's define here the median that we're going to graphically represent refraction. So we have air and we have water. So water is more dense than air. So that's the reason why the light waves is going to slow down, because it's going to a more dense area. So if we didn't have those two different medians, this fish guy here will target the right fish. But because we have two different medians, this is not going to happen. The light is going to bend, and the real location of the fish is below the one that is observed. So how we represent actually graphically a situation like this? So we know that waves, they come in like wavefront. So wavefront here is represented those parallel lines. They are the crests, and this is the incident ray that is perpendicular to the wavefront. We need to define our boundary, and we need to define our normal line. So here we have our refracted ray, which is bent. We are going to take a look if it will be bent toward or away the normal line later. So this is the normal line, this is the boundary, this is the incident ray, and this is the refracted ray. And this is the angle of refraction, and this is the angle of incidence. So those are the variables that we need to include in our diagram when we represent graphically a refraction of a wave. Now, we need to observe too the wavelength. The wavelength reduce, the wavelength get bigger. We are going to go with more detail later. Okay, so when is the refracted ray away or toward the normal? So here we are going to show two examples to differentiate this situation. One is when a wave moves from one area that is less dense to an area that is more dense. So a light, for example, is coming from an area with less particles. So the minute that moves to an area with more particles is going to slow down. When it slows down, it's going to refract towards the normal. So less dense to more dense, the wave is slow down. So one acronym to remember this is FAST. So fast, but you are not going to include the A, FST. So fast. So fast to slow toward. So come fast to slow. The refracted ray is going to be toward the normal. Now let's see the opposite situation. The wave comes from area more dense to an area that is less dense. So what is going to happen here is, okay, so not that many particles, so this is going to speed up, it's going to move faster because there is not that many obstacles on this area that is less dense. So more dense to less dense, the wave is going to speed up. One acronym to remember this is SOFA. So SOFA, you are going to exclude O. You'll be slow to fast is away from the normal. Okay, slow to fast, away to the normal, away from the normal. I'm sorry. Okay, now we're gonna study, verify. This is kind of a little bit long lab, but it's a really critical lab to understand the law of refraction that is also named as Snell Law. So we're going to look with more details, but I'm going to work with you here step by step on how to set up this lab and all the variables, how you're going to put together, and the conclusion that you are going to have from all these about the refraction. So the materials that you need for this lab is the semicircle acrylic tray, a protractor, 3 pins, a ruler, an angular grid, a piece of cardboard, and water. So first, on your grid paper, you are going to draw a horizontal line and a vertical line, just like it's showing in this paper. Then you are going to inspect the tray to find the scratch line. So you need to identify this scratch line. And then you are going to place the tray on the center of the grid paper, just like it's showing in this picture. And you are going to place a pin in front of this tray right on the scratch line. And then you are going to fill the tray with water. So we are going to practice first. So our first example, you are going to practice, and then you are going to proceed with the other steps based on the first one. Is very critical, the way that you are going to set up. So let's practice first. Place a pin into the cardboard a few inches in front of the tray on the flat side, right on the vertical line on this grid paper. You are going to mark the pin location a letter A. Okay, then on the other side, on the curvy side, you are going to look at eye level through the water, and you are going to locate when the pin is going to align with that one that you place by the scratch line. So all those 3 pins align. You are going to mark on the pin that is front of the curvy side A1. So A1. you are going to repeat the same procedure 4 times. So let's look at the next slide. So here is the repetition that you are going to have. I will have to do all this repetition. I'm not going to read this for you, but I'm going to show you graphically how you are going to set up this. Okay, so on the flat side of the tray, you are going to use the grid paper and the vertical line that we are going to call normal line, and you are going to identify all those 4 angles, 20, 30, 40, and 60, away from the normal line. So if this is the normal line, your 20 will be 1, 2, 20. 30 will be here, 40, 50 is here, is not marked, and 60. So you mark all angles that you are going to be working in this lab. So next, you are going to label all these marks A, B, C, D, and E. Now, what you are going to do is, one by one, you are going to look through the curvy side of this tray and align the pin from the other side with the pin that is marked right here by this flat side of the tray by the center, and you are going to find the corresponding image on the other side, but you need to look through the water. So you already did A1. You're going to do the same thing with B, and you're going to find the location of the pin, and you're going to mark B1 and C, C1, and so on. So then you are going to remove the tray, and you are going to use your ruler, and you're going to draw a line that is going to connect A1 is easy, but B, with B1, you are not going to draw a line that connect both states. You need to draw a line that connects to the center first, and then to B1, just like shown in this picture. B with B1, C with C1, D with D1, and so on. So I'm going to show you graphically how this is going to be done. So here we have B, C, D, and E. So you're going to connect B with B1, C with C1, D with D1, E with E1. Now what you are going to do is you are going to measure the angle these points they are going to make with the normal on this side. For example, okay, so B is making 15 degrees with the normal, because all this here, all this vertical line is the normal line. So B is making 15 degrees, C is making, C is 30, right? C is making 30 degrees, 22 degrees actually, because C is right here at 30, 10, 20, 30. But the correspondent on the other side is making 22 degrees with the normal. As you see, each line refracted, you see, is refracting. Now we have 40 degrees. This one is 40 degrees, is making on the other side 30 degrees. So 10, 20, 30. The one that is at 60 degrees, you'll be at 45 degrees with the normal. Now that you have all these angles, you are going to include one more column, this one, and you are going to use your calculator, and you are going to divide those two values. So those two here will be undefined. 20 divided by 15 is 1.33. 30 divided by 22 is 1.36. 40 divided by 30 is 1.33. And 60 divided by 45 is 1.33. Now we are going to plot a graph with the angle of incidence on the x-axis and the angle of refraction on the y-axis. So we are going to connect those two relationships, 0, 0, 20, 15, 30, 22, 40, 30, 60, 45. And we are going to draw this line. So we have this straight line. So what that means? Okay, what that means is that these two quantities form a straight line on a graph. So then a mathematical relationship can be written in this form. So y is equal mx plus b. The y is our angle of refraction and the x is the angle of incidence. The m is the slope or the gradient that we already calculate here, which is 1.33. We have this off here, 1.36, but the average will be around 1.33. So our m, which is our slope, is 1.33 and x, and b is 0 because this is a straight line graph. So what that means is, with all these that we did, with this angle and the refracted angle that we measure using the water tray, is what is given to us is the angle of the index of a refraction. So the index of refraction reflects how much a light wave bends when traveling from one medium to another. So here we have a table with very common materials and their index of refraction. For example, vacuum, there is no bend of the light. The light goes straight in a vacuum. Air is about the same of the vacuum. Water is 1.33. That's incredible because that's what actually we calculate in our experiment. 1.33 actually is the index of refraction of water. And here we have ice, glass, and diamond. Diamond have a very, very high index of refraction, so which means that bends a lot. So the result of this lab experiment proves the index of refraction of water is 1.33. Okay, so what else we can conclude from this lab? We have this relationship here. Y is equal 1.33x. Our y is the angle of refraction and our x is the angle of incidence. So we can kind of find a relationship with a trig function that will be something like that. You know the index of refraction of the air is 1, and we know these values here, 15, 20, 22, 30, 45, are the angle of refraction. So we have here 1 time sine of the angle of incidence is equal to 133 sine of the angle of refraction. So this relationship is called Snell's law. So Snell's law states that the index of refraction of the median, in this case, in this example, the air, times the sine of the angle of incidence is equal to the index of refraction of the second median times the sine of the angle of refraction. So this is the conclusion of the lab actually. So let's do a couple of practice problems. A straight glass rod appears to bend when placed in a beaker of water, as shown in the diagram below. So here is a glass rod, this is air, this is water. So what is the best explanation for this phenomenon? The water is warmer than the air. Light travels faster in water than in air. I don't think so, because here water is denser than air. So light will travel slower in water than in air. Light is reflected at the air-water interface. If it was reflected, so it will go straight, because that's what the law of reflection states, that there is no bend. Light is refracted and it crosses the air-water interface. I will say this will be the right answer. Now, the next example. For the diagram below, find the index of refraction N2. So we have here this example. Very simplified form. You see that you don't see wavefronts anymore. You just see the incident ray and refracted ray, the angle of incidence and the angle of refraction, and the index of refraction of this median and the index of refraction of the second median. We don't know which median are those. I just say the value of the index of refraction. Okay, so we are going to use this Nells Law to find the index of refraction on the second median. So the first median is 1.5 times sine of 45, and the second one is N2 sine of 65. So you need to use a calculator, and the 1.5 times sine of 45 is 1.06, and 2 times sine of 65 is 0.906. So you divide both values, and your index of refraction for the second median is 1.17. So that's all for today, and thanks for watching. And this is a long video. I will suggest that you go back and take a look again with all those things that you learned today.